Welcome to this explainer for Case Study '06. If you're watching this, you're probably gearing up to spend a solid 2 to 4 hours this weekend working through the labs. As your TA, my goal right now is to orient you. Before you write a single line of code, we're going to look at detecting modular structure in complex engineered systems. We need to understand what a design structure matrix, or DSM, actually is, and what it's telling us about our engineering architecture. Let's start with a concrete engineering scenario. Imagine a sudden failure in a drone or rocket system. A critical sensor goes offline, or maybe the main power bus faults. As a systems engineer, you immediately need to know exactly how that single fault propagates through the entire architecture. The central question you're asking is, which component, if it failed, would trigger the largest system-wide cascade? Answering that requires us to actually see the deep coupling in our system. Take a moment to look at this grid. When you first look at an unclustered design structure matrix like this, the coupling is basically just an unreadable hairball of dependencies scattered across the rows in columns. A mark from row I to column J simply means component I depends on component J. But staring at this raw matrix, you can't easily see the distinct subsystems. The modules are completely hidden. It's just noise. And that brings us to our core professional skill for this case study, measure. Throughout SYSN 47D, we focus on 4 key skills: identify, measure, infer, and predict. Here, we're measuring. We're moving way beyond naive spreadsheet lookups to quantify the actual structural modularity of our system. We want to use algorithms to automatically uncover those hidden structural seams, the boundaries that separate, say, a propulsion system from a telemetry system. Part 1, the sketchpad moment. Before you touch the interactive tool or open your coding environment, I want you to step away from the keyboard. The real thinking happens on your sketchpad. The tool is just there for verification. So, grab your marker. First, pick a rocket, a drone, or a software system. Map out 8 to 15 nodes and draw the dependency arrows between them. Then, draw a blank 8x8 grid. Try to construct your own predicted matrix by hand, filling in the cells where you think a dependency exists. Right after you finish that sketch, you're going to realize something fundamental when you compare your hand-drawn matrix to the real one. Drawing circles and arrows feels really intuitive, doesn't it? But it actively hides the deep coupling of a system. A matrix, on the other hand, cleanly exposes it. A node-link diagram can make a tightly coupled system look perfectly manageable, but a DSM tells you the harsh truth about your dependencies. Part 2. The interactive exercise. In the browser-based lab, you're going to spend a few minutes dragging rows and columns by hand, trying to visually isolate modular blocks. You will quickly experience the combinatorial nightmare of doing this manually. Every swap that fixes one module almost certainly breaks another one. You get trapped in local minimums. And this brilliantly illustrates exactly why we rely on community detection algorithms like Louvain. They optimize modularity globally, instantly finding that hidden block structure you missed. The search space is simply too massive for manual sorting, even on a small 18-component drone. While in the interactive lab, you'll also run a failure cascade simulation. You'll click on the electrical power system in the Rocket DSM, highlighting its forward cascade in a bright mustard yellow. You'll trace how that failure propagates through avionics, GNC, comms, and ignition. Now, I'll let you figure out the exact scale of that cascade for yourself, but pay close attention to how a quote-unquote subsystem failure rarely actually stays within its subsystem. You'll also take a close look at the residual off-block marks for each system after the algorithm does its best clustering. For example, you'll calculate exactly what percentage of a software architecture retains its marks entirely outside of the clustered blocks. It stubbornly resists clean modularization. Keep the number you calculate in mind because it sets up the most important conceptual takeaway of this entire week. Part 3, the coding exercise. Once you've built up your intuition, you'll open up your Python or R environment to apply these concepts to a synthetic 200-component engineered system. Here is the pipeline you're going to write. Your script will build a directed graph from a long-format edge list. You'll run the Louvain and fast-greedy algorithms on the undirected projection to maximize modularity. Then, you'll score the resulting partition against the ground truth using the adjusted RAND index. Finally, you'll reorder the adjacency matrix by module membership to visually verify that clean, block diagonal structure. Now, this is the crucial point. This is the core misconception this case study is designed to dismantle. A lot of engineers assume that perfect, clean clusters equal a good design, and that off-block marks mean a messy system. But high residual off-block marks aren't always a sign of bad design. Instead, they reveal structurally cross-cutting components, things like physical power lines or software authorization and logging. These intentionally bleed across modules. No clustering algorithm can fix them because they aren't a bug, they are the architectural reality of the system. Which brings us to your final task right before you start the lab. Grab your pen and your sketchpad. Here is your prompt. Sketch a 15-node graph of an engineered system you know well. Physically draw the seams, the boundaries separating it into communities. Now, highlight the bridge node in mustard yellow. Which node, sitting right on that boundary, holds the clusters together? If you removed it, exactly how would your clusters fragment? Draw that out, think it through, and then jump into the case study. I'll see you in the lab.